Hello, and welcome to the very first episode of The Nameless Show. I am your humble narrator, the Madman, and today we're going to be looking at a video called Our Flat Domed Closed System Explained by DMurphy25. Not sure if that's D. Murphy. If it is, hello, sir. The reason why we're looking at this particular video is it was submitted to my Facebook group, the Spherical Earth Society, for commentary, and so I thought I'd break it down episodically. It's a long video. Who knows how many episodes it'll take? Let's get going.
Thing that really got me interested was, as you say, the gyroscope. In a plane, there is an artificial horizon, okay, and it's based on a gyroscope. And if you spin a gyroscope...
Okay, so this is a basic gyroscope. And a gyroscope is nothing but a spinning top inside a special frame. So here's your spinning top. Whenever you spin a top, it wants to point straight up into the sky and straight down toward the center of the Earth. Okay, straight up into the sky, straight down toward the center of the Earth. All right, and the spinning top is in a frame that allows it to, the frame can move back and forth while the top continues to point straight up in the sky and straight down toward the center of the Earth. All right, then that frame is connected to another larger frame that allows it to roll forward and backward. So no matter how you twist this frame around that spinning top, the top always points straight up at the sky and straight down toward the center of the Earth. Now let's look at a gyroscope as it exists in an airplane, since that's what we're talking about. All right, so we're going to take a look at a gyroscope in a Boeing 747. And this is the Sperry vertical gyroscope for a 747. And as you can see, it looks a heck of a lot more complex, but it's really the same thing. In this central housing, you have an axle with a spinning mass. That's your top. Okay, and then that housing is connected to this frame, which gives you your first additional axis. And then that frame is connected to this frame, which gives you 3 total axes, which is what you need. When the power is applied to this box and the center mass starts spinning, everything rolls up into place very nicely. Here is a detail shot of some sensors that will end up transmitting the relative position of the gyroscope as information to a gauge in the airplane's dash, and that gauge is called an artificial horizon. Okay, and there's the armature and flywheel that actually get the mass spinning. All right, so let's take a look at artificial horizon gauges. All right, so as you will notice, different model gauges are still quite similar. The sky is always blue, the Earth is always brown, and there's always a line in the center that denotes the horizon. Okay, so above the horizon, that's the sky, and below the horizon, that's the Earth. All right. Now, if the plane's flying level, then the gauge should be level with the horizon. All right. However, if the nose of the plane is pointed toward the Earth, then the gyroscope is still trying to face straight up and down, but the plane's pointed toward the Earth. So that difference is translated into the gauge. If the plane's nose is pointed at the sky, like on this gauge, and also taking a slight left turn, then it's above the artificial horizon. The plane is above the horizon, so it's climbing, and it's also turning left a bit in this picture. Right? So does everybody understand that the gyroscope acts like a gyroscope, and then sensors transmit the information to a gauge in the dash? Simple as that. And let's take a look at an actual Boeing 747 cockpit so you can get an idea of how complex these things are, and maybe get a little perspective on the people who are flying you around. This is the cockpit of the airplane. As you can see, your average person would not even be able to figure out how to turn this thing on. Anyway, that's your artificial horizon gauge. And it's below it is an altimeter, it looks like. And among the gauge cluster, you have all your radars, your comms, you have your brakes. Right in the center there's your throttles for your engines. Up here is various switches for subsystems that have to be turned on before the plane can take off. You have trim surfaces, you have flight control computers that have to be turned on. So this plane is packed full of electronics.
on a surface, it will want to stay upright. You can twist and tilt the surface as much as you like. The gyroscope will stay upright. So, if a plane has a gyroscope and it starts following the curve of the Earth, the gyroscope would stay upright, which means the artificial horizon will start to roll backwards.
The artificial horizon will not roll back, and here's why. This is a model of a round Earth, and let's say that a plane is flying across the Earth. In fact, for illustrative purposes, let's say that this frame around the side of the model represents the flight path of a plane going from the North Pole to the South Pole on a theoretically round Earth. At the North Pole, the gyroscope wants to point straight up into the sky and straight down through the center of the Earth, just like we've been talking about, okay? When the plane gets out here, then that orientation is changed. Now, straight up into the sky is here, straight down through the center of the Earth is here, okay? When the plane gets down below the equator, orientation has changed, and it's constantly changing, up in the sky and down through the center of the Earth. And finally, when it reaches its destination, it's still straight up into the sky, straight down in the center of the Earth. So as along this plane's flight path, what is up and down is constantly changing as the plane moves, and it's changing very slightly as the plane moves in relationship to the center of the Earth. So the horizon always stays nice and steady as long as you're flying at a steady altitude, and you don't have any rolling of the gauge. If the gyroscope's not moving drastically, the gauge isn't moving drastically, because the gyroscope controls the gauge. Okay? And that's why it won't roll back, and it doesn't roll back.
But it doesn't. That's absolute proof that a plane flies over a flat surface rather than a curved one.
No, it's not,
Because,
and we
I
know
asked
exactly
the
why.
pilot on my last flight, do you ever notice the artificial horizon rolling backwards? He said, no, but the artificial horizon has complex electronics in it to make sure it knows where it is on the Earth and it compensates.
Okay, let's take a second to refresh what we know about gyroscopes in airplanes. There's the gyroscope connected to all of its frames. Oh, incidentally, these little axles on the side where the frames are connected, they're called gimbals. Okay, and these are the gimbal position sensors, all right, that tell the gauge in the dash where the gyroscope is and allow the gauge to adjust. And that's your armature and flywheel, the masses. All right, here are your gauges again. Once again, your artificial horizon gauges, just confirming everything that we know about these gauges. All right, so the gyroscope conveys information to the gauge through electronic sensors.
But I went to the manufacturer of the artificial horizon, and they confirmed to me that it's completely mechanical, nothing electronic in it whatsoever.
Okay, so at this stage of the game, the video has taken an unfortunate turn. We started out with some nice factual information about gyroscopes, transitioned into what could be construed as a simple misinterpretation of how a gyroscope works, but now this gentleman is lying to me, and I don't understand why he would do that in trying to advance this flat earth theory. Why would you need to contact the manufacturer to begin with? We already see that a simple image search will give you all the details on the kind of gyroscopes that are in modern airplanes and how they work, and the electronic sensors that connect them to the gauge, in the dash of the airplane. So I don't understand why this gentleman would sit here and try to insist that there are no electronics involved with the gyroscope in an airplane. I just don't understand why he would make that statement. It's simply not true.
So it's literally just a gyroscope that can freely move. So that right there is proof to me that planes fly over a plane. None of it makes sense. The problem is that we're taught as children, this ball earth lie.
Okay, so let's talk about this for a second. So having talked to a number of folks who espouse the flat earth, It's my understanding that the purpose of the whole conspiracy and cover up and lie about the shape of the Earth is to conceal the truth of God and God's creation. So my questions would be, how could that happen? How could any number of humans, no matter how rich or powerful, hatch such a conspiracy against an infinite, all-powerful, and all-knowing being? And if in fact the vast majority of the people on the planet do believe a lie, then why would a benevolent God allow that to continue? It's not like they have free will. They were told a lie. They trusted their parents, they trusted their teachers, and they believed the lie. So free will doesn't enter into it. So these are some of the philosophical questions that this issue engenders. And I would love to hear comments on that from anybody who espouses the flat Earth.
And, you might ask as a child, what about the people in Australia? They're standing on the bottom of the globe, won't they fall off? And your teacher says, no, gravity. And you go, oh, okay. And you never go back to that question. But when you go back to it as an adult and start looking at it with a critical eye, right, the whole thing falls apart. As you say, the globe is spinning at 1,000 miles an hour.
Okay, so let's talk about the spin of the Earth. Now, 1,040 miles an hour sounds like fast, sounds like something that you would fly off quite easily, but in reality, when you compare 1,040 miles an hour to the circumference, that is the distance around the spherical Earth, you'll find that circumference is around 24,860 miles, I believe. And if you divide the spin of the Earth by the circumference of the Earth, you'll find that that coincides neatly with 24 hours, which is why it takes 24 hours for a landmass to go all the way around the spherical Earth and come back to the same position. Thus, we have night and day. All right? So it's not a big mystery. Oh, and also I would point out that you have always been spinning at 1,040 miles an hour. It is the only sensation you have ever known. So if there is a sensation, all human beings are used to it, because your parents felt it when they were conceiving you, and your mother felt it when she was carrying you around, and it's all you've ever known. The only sensation that you have ever known is the spin of your planet.
Neil deGrasse Tyson, who's a leading astronomer in America.
I'm Neil deGrasse Tyson, bitch.
Love that guy.
Tells us that the Earth is not a perfect circle. It is actually an oblate spheroid. It's squashed and wider at the equator. Yeah.
So Earth, throughout its life, even when it formed, it was spinning, and it got a little wider at the equator than it does at the poles. So it's not actually a sphere. It's oblate. And officially, it's an oblate spheroid.
Okay, so this is a very important point. This is an oblate spheroid, but nobody is suggesting that the Earth is flat and squashed like this. In fact, it's only 14 miles shorter north to south than it is wider east to west. So it's a very, very slight difference north to south than east to west. It's only 14 miles. That would be 7 miles north or 7 miles south of the equator shorter than it is wide. So it's a very slight, oblation, I guess is what you would call it. It is almost spherical. It's just it's just not quite as tall as it is wide.
That's what we call it. But not only that, it's slightly wider below the equator than above the equator.
A little chubbier.
A little chubbier.
Yeah.
Chubby's a good way. It's like pear-shaped.
So my question to him would be, why is there land at the equator? Because water will move more readily than rock. So if the Earth is spinning, the water will be collected at the equator. I mean, if you spin a wet tennis ball, okay, you spin a wet tennis ball, the water shoots off.
Okay, so let's unpack this, because there's quite a bit to unpack. So this guy's saying that he believes that if the Earth was spinning and had formed while it was spinning, then there would be no land at the equators. It would all be water. Okay, and here's why that's wrong. When Earth was first forming, it was a super hot ball of gas that, because it was flying through the intense cold of space, started to cool down. and that gas started to turn in slowly into a molten solid like lava, a big molten ball of lava, which continued to cool in the cold of space, so that the outside eventually dropped to be cold enough to where it actually started to become solid. And we know that today on Earth it happens at no cooler than around 700 degrees centigrade. Okay, so that's very hot. That'd be like well over 1,000 degrees Fahrenheit. Um, so at any rate, um, the rock and metal that forms Earth's crust were already solid and in place before the Earth cooled enough to be around 100 degrees centigrade, which is where it has to be for water to turn into liquid and actually start to think about falling from the sky. Okay, so the rock and the land at the equator was already in the way before Earth cooled down so that water could actually form and fall as rain and then do what water does, which is flow into the lowest place it can. All right, so and this is a terrible picture. It does a good job of illustrating what might have happened in the primitive solar system. But so, for instance, by the time Earth formed and water could fall, this over here might be a mountain that wouldn't have water on it. Okay, and this seam in the center of the ball here, um, it might be like a river. It's a low point, so you might have water flowing through that as a river. Okay, so and that's how it works. By the time Earth was formed, a lot of the features on its surface were also formed, and the water had no choice but to fall down around it. So that's why you have land at the equator. It's a pretty simple explanation, actually.
At the equator, essentially. So all the water will be gathered around the equator. So why is there land at the equator?
We all understand.
Doesn't make any
why,
sense.
Hopefully. Anybody who doesn't, leave a comment.
The other thing that about the spinning Earth is looking at the stars. Now, directly above the axis of spin is the pole star, Polaris, okay, directly over the North Pole. And we're told that the reason that all the stars spin around the North Star is because the Earth is spinning at 1,000 miles an hour.
Okay, so let's unpack this as well. In fact, that is exactly the reason. The stars are not spinning this way. Earth, if this is north, okay, then south is going to be directly below you, and east is going to be off this way. And in fact, the stars are not spinning this way. Earth is spinning this way, and that's why when the sun comes into view, let's just say, not out to scale or anything like that, this is the sun shining down on Earth. Earth spins this way, and that's why the sun appears to rise in the east and travels across our sky until it disappears again and it's night. And that just keeps happening in 24-hour cycles.
Okay,
over and
seems
over
to
again.
make sense, because if you put a long exposure camera pointing at the North Star, you'll see the stars will make perfect circles around.
Okay. Okay, so I would dispute the notion that these are perfect circles. I'm sure with delicate enough instruments you could detect tiny variations. They only appear to be perfectly spherical to our eyes. But one thing is that our star is one of many stars in a galaxy called the Milky Way that's moving away from the center of the universe, and all the stars in that galaxy are moving in roughly the same direction at roughly the same speed. Okay? That's a very important concept to understand.
Perfect star trails. The only problem is the Earth is also orbiting the Sun at 67,000 miles an hour. Okay, the Sun is moving, dragging the Earth and all the planets up that way or that way at 600,000 miles an hour. So why do we see perfect circles? You know, because that's the slowest speed.
Okay, so again, I would dispute that those are perfect circles. I'm sure with delicate enough instruments, you could discern variations in how they're spinning. But in any event, this is a diagram of the solar system moving through the galaxy. Okay, so the sun is indeed moving out from the center of the universe at 600,000 miles an hour, and it's dragging all the planets behind it, and Earth is moving around it, and Earth is also spinning. as crazy as that sounds. But with all that motion, the distance to other stars, well, first of all, like I said, all the other stars that you can see with your naked eye are in our galaxy, and therefore they're already moving in about the same direction at about the same speed we are. So all these stars are moving in the same direction as the sun is at about the same speed. Stars that are closer to the center of the universe are moving a bit slower. Stars that are the farthest away from the center of the universe are moving a bit faster, but they're all going about the same speed. All right, so that's a very important concept to understand. Another thing is distance. The stars are immensely far away, and if you do a simple experiment with your smartphone camera, just zoom it all the way in, then find an object, look at it from 10 feet, 50 feet, 100 feet, 500 feet, and 1,000 feet. Notice that the farther away you get from it, the less any motion of your camera affects how the object appears to be moving in the field of view. All right. So the farther away you are, the less that the motion of your hand should
at
affect the camera.
600,000 miles an hour.
All right. So again, yes, even though the sun is screaming through space and dragging the planets behind it, and it sounds all violent and brutal, to us it's rather, gentle, um, because Earth is heavy and it's exerting its own gravitational pull, and it's nicely balanced in an orbit around its star, and it's not going anywhere. So even though, yes, we're moving through space at insane rates of speed, we don't feel any of it, not a bit of it. But at any rate, the reason why the stars don't appear to move around much is that, again, they are moving in this approximately the same direction at approximately the same speed, and as the Earth travels around the sun, that's why different constellations of stars are exposed to you in the night sky. So depending
So
where you
why
are
do we
on Earth,
see perfect circles?
not perfect, depending where you are on Earth, you'll see different stars at different times of year, because the Earth is traveling around the sun, and that's giving you access to view different constellation of stars that were hidden before by the sun's orbit. Okay, and that's why the constellations change in the night sky. And again, if you had sensitive instruments, you could dive in on the tracks of these stars around Polaris, the North Star, and I'm sure you would see tiny variations due to the motion of the Earth around the sun and due to the wobble of the Earth as it spins on its axis, which has like a tiny little wobble. All right, tiny little wobble in comparison to, again, the vast, vast hundreds of billions of trillions of miles in between us and the stars around us, just so far away. And that's why, no matter how much the quote-unquote camera shakes on this end, up in the sky, the stars appear rock solid. It's a matter of distance, and it's a matter of the relatively small motion of the Earth around the sun compared to the distances to other stars, which again are, traveling along with us in our journey away from the center of the universe. And gosh, I thought I had more to say about this, but apparently I don't. Although, judging by the cursor, me somewhere is excited about it. We're going to pick up with audio again here in a second, and I apologize.
Because that's the slowest speed, that's slowest motion in that mix, and yet the Earth is moving 67 times faster that way, and 600 times faster that way. So you should see the stars do all sorts of strange motions, but you don't. You only see them make these perfect circles. That tells me that it's the stars that are moving, not the Earth.
Okay,
the thing is, what the scientists will give you is...
All right. Okay, so now we have to talk about the implications of the spherical Earth and something that is also proposed as part of the spherical Earth called gravity. Now, as I understand it, Flat Earth says that there is no such thing as gravity, and that the various forces that we observe on Earth, like weight and the tides and waves and stuff like that, are caused by magnetic fields. So there should be a simple way to test and see if that hypothesis is true. So I propose an experiment. What you'll need for this experiment is a clear receptacle for some water, something that holds about 8 ounces, preferably with straight sides. Doesn't matter what it's made out of, so long as you can see through it. You'll need some distilled water if possible. If not, tap water is okay. You will need some salt and a way to measure some salt into the water. Okay, so what you're going to do is take your clear glass, whether it's plastic glass, doesn't matter. You're going to fill it up about halfway. If it holds 8 ounces, that should mean you have about 4 ounces of water in it. Oh, and you're also going to need a magnet, a relatively strong magnet, something that'll pick up at least 5, but preferably 10 pounds. If it'll pick up 10 pounds, that means it's 40 times strong enough to move 4 ounces of any substance that it's attracted to. And so you should get a nice clear result with a 10-pound magnet. So with your glass half full of water, you're going to move the magnet up and down the side of the glass. Now, if the magnetic field from the magnet can affect the water, then that water should tilt. Okay? So if you move the magnet up the right side, the water should be drawn up the right side, and it should tilt upwards to the right, like that. Likewise, if you move the magnet down the side of the glass, okay, down the side of the glass, then the water should pull the water down on that side and tip it up and to the left. Okay? So if you move the magnet up and down the side of the glass and observe that effect, then you can be confident that a magnetic field has a substantial effect on moving water. And if you don't, then you can conclude that a magnetic field does not have a substantial effect on moving water. Now go ahead and ladle a nice teaspoon of salt into the glass, stir it in, and repeat your experiment. That way you can kind of duplicate conditions as they might exist in the oceans of the world. And again, if you observe an effect with the magnetic field, then that means magnets can cause the waves and the tides. If you don't observe an effect, that means magnets cannot cause the waves and the tides. And you must search for another conclusion, another force that's causing things like the waves and the tides.